Thank you. Thank you. Good afternoon, everyone. There has been a huge interest in today's program, so greetings to everyone who made it in the main room and also to all the folks in the overflow room next door. This is truly a special event. It's one of several in our celebration of Stanford Engineering Centennial. Were any of you at our party a couple of weeks ago? Yeah, that was we had quite a party on the main quad. It was truly, I'd say, a once-in-a-century celebration. For today, I'm sure you're all very anxious to jump into a timely and important topic, and that's AI and the future of computing. But first, indulge me in a little bit of history. A century ago, Stanford had 4 engineering departments, and all of those 4 departments were actually created in the very earliest years of the university. They were civil engineering, electrical engineering, mechanical engineering, and mining and metallurgy. Sort of became materials science and engineering. In May of 1925, the Board of Trustees approved bringing those 4 departments together into a school. And at that time, the trustees and the faculty, I don't think they could possibly have imagined today's smartphones, supercomputers, or artificial intelligence, but they were thinking about the future. They knew that engineering would be central to progress. They knew Stanford had a unique role to play by combining technical rigor, but with broad-minded curiosity, by educating engineers not just to design and build things, but also to lead and to have impact. And this centennial year is a chance to reflect on the incredible arc of progress that we've made since 1925. There were breakthroughs in microwave radar, in power transmission, and then later semiconductors, the birth of Silicon Valley, more recently bioengineering, sustainability, and of course, artificial intelligence. But it's also a chance to look forward, and that's more what today is about. So we've invited researchers and leaders in computing and AI to help us understand what's on the horizon. It is very well established that Stanford Engineering has played a major role in shaping the computing era. From very early innovations in electrical engineering to the creation of the first internet protocols, from pioneering work in multi-core chips to the rise of AI and deep learning. And that legacy continues today with our faculty and our students doing cutting-edge research and our alumni holding key leadership positions. Now, with that technical progress, of course, becomes responsibility. We need to think about where we're headed, the impacts of it on society, how we can lead in ways that are thoughtful and collaborative. And I would say there's no better place than Stanford to have that conversation. And probably really no better moment than now. The power and reach of computing, data, and AI are growing at unprecedented speed. So you're going to hear today about advances in chip design, system architecture, next-generation AI models. You'll hear from academic leaders, industry leaders who are helping to shape the national strategy and also think about the global impact. And I hope today you'll come away with a deeper sense of how Stanford Engineering, through research, through education and partnerships, is helping define the future of computing and AI. So thank you again for coming. We have a very exciting program ahead. And to kick things off, I'm delighted to introduce someone who brings extraordinary perspective and deep insights into society and policy aspects of computing and AI, and frankly, anything she thinks about. I'm pleased to introduce former U.S. Secretary of State, former Stanford Provost, now the director of the Hoover Institution, and my personal favorite of her roles, co-chair with me and others of the Stanford Emerging Technology Review, which she will tell you a little bit about. So please join me in welcoming Condoleezza Rice.
Thank you very much, and welcome to the Hoover Institution, which is where you're seated. But I just want to join everyone in congratulating the School of Engineering on 100 spectacular years. And even though most of us won't be here, I'm sure that there will be another spectacular 100 years ahead. Because what Stanford has achieved in engineering is just so extraordinary. But it's largely because of the people. This university and this School of Engineering has brought the best talent, the best minds, the most creative minds, from the 18-year-old who comes here as an undergraduate to study, to the graduate student who comes from across the world to study, to the folks in the lab, the faculty, the investigators who put it all together. And I think one of the wonderful things about this campus is that we put it all together on this campus. And that is the reason that Jennifer and I have been able to have this major project called the Stanford Emerging Technology Review, which the two of us lead on behalf of the university. And the idea is very simple. The technologies that we are now seeing breaking forward, certainly AI, but also in robotics and in space and in bioengineering, are, as a colleague of mine calls them, civilizational technologies. These are technologies that have the potential to transform just about everything about the way that we live, to transform it hopefully for good in terms of education and in healthcare, in national security and in society. We all hope that these technologies will be indeed for good. They also, of course, have challenges to our institutions and our societies, and I have to say that sometimes human beings have been better at the knowledge part than at the wisdom part. And given the nature of these technologies, the wisdom part is going to be very important. And so in the Stanford Emerging Technology Review, we've done something that we think is a little different from the way others are studying technology and policy across the country, which is that we actually have brought the scientists who are at the bench in the labs into conversation with economists and with national security experts and with education experts and with healthcare experts to really understand how these frontier technologies can affect society for good. We also believe that this is a time when policymakers have to understand these technologies, at least at a rudimentary level, so that they can create policies that encourage innovation, that do not stop innovation, but that are aware of what these innovations may mean. I think it's fair to say that in Washington, D.C., they've now learned to spell AI. Whether there is much more right now to the understanding, I think, is questionable. And so through the Stanford Emerging Technology Review, which has now been launched twice in Washington, D.C., at the White House, with the intelligence agencies, at the Pentagon, at the State Department, we hope to encourage policymakers to become more conversant about what these technologies are, what they will do, and to do so by having access to our scientists. And it certainly helps that my office is right over there in the Schultz building of the Hoover Institution, but I can walk, and in 15 minutes I can be with the best computer scientists and the best roboticists and the best bioengineers, and we have to thank Senator Stanford for that. He gave us enough land that we're all on the same campus, and that's something that we value. It makes it possible to do the kind of work that we are doing, and I just want to thank Jennifer for her leadership of the Stanford Emerging Technology Review. We started with just some conversations with engineering faculty about their vision for how to have policymakers understand these frontier technologies, and now we're a little more than 2 years into it, and it's been really one of the great, really most fulfilling things that I've done in my career, is to bring Stanford technology to those who we hope will create the systems, the funding, I want to emphasize funding, and the opportunities to push those frontiers forward. So thank you very much again. Congratulations on the centennial of the school. And now I'm going to go to my seat and get educated. Thank you very much.
Thank you, Condoleezza. When I'm asked what's special about Stanford Engineering, I always mention that we are in a liberal arts university with professional schools, with the Hoover Institution specialists in policy. We have opportunities to collaborate in ways that I believe no other school of engineering can, and we always do our best. And the Emerging Technology Review is a perfect example of that type of collaboration. So now we're going to dive into the heart of the research. So we're going to go from chips to systems to applications with 3 of our amazing Stanford engineering faculty. First, we're going to hear from Srabanti Chowdhury. Her work on advanced chip materials and energy-efficient hardware is helping to make AI more sustainable at the source. Then we'll hear from Kunle Olukotun, who is a true pioneer in parallel computing, and we're going to hear how new architectures are breaking performance barriers and enabling new types of computation. And then finally, Carlos Guestrin will take us into the frontiers of generative AI, where models are becoming more adaptive, more reliable, and more capable of reasoning. So these 3 talks are just going to give you a small taste of the incredible innovations that are happening across Stanford engineering as we launch into our 2nd century, and I know you will enjoy them.
The world has seen the progress of lighting, from the warm glow of the incandescent bulb to the compact fluorescent lamps, all the way to the bright white light of LED, which might be shining right above you. This was not just about the brightness, it was about efficiency. What was 90% wasted heat in an incandescent bulb to only 10% of the energy converted into light, it became 90% light in a LED to only 10% heat which was wasted. Huge transformation in energy efficiency. But more important, this technology became affordable, and that made the big difference. Now, what you may not have known, what happened behind the scene. Oftentimes, there are materials that unlock potentials of a technology, and in this case, it was gallium nitride, the blue LED, the blue light material. Now, before 1990, this gallium nitride, the special material which had the capability to emit blue light, used to grow in columnar defective form, the one that you can see with very high power microscope, and you can tell which one it is, the columnar one, riddled with defects, grain boundaries that trapped light and did not make blue emission efficient. After 1990, thanks to a materials breakthrough that made it planar, flat, smooth, and was the real reason when blue light became efficient, which is why you enjoy the white light that you see today. Such is the power of materials breakthrough. Now at Stanford, my group worked on chasing this efficiency. We try to maximize efficiency at the device and the materials level that scales all the way to the system, something that you can feel, something that end users can enjoy. As such, we work on improving frequency, boosting bandwidth, making things more power efficient. But over and above all, we are tackling a critical time-sensitive problem, which is heat. We do thermal management, and that's the conversation I'm going to have with you today. Impact truly begins with framing the problem correctly. And speaking of the problem, as we get more power hungry from our chips, well, you pay a cost, and that is heat. As the processors become faster and more powerful, the cost you are paying is it gets hotter. Very hot that we are almost shooting for the sun instead of the moon. So for instance, now we are no longer in the flat, plain, two-dimensional processes, which used to be very well managed thermally by a technology called heat sink. It did wonderfully well, but not anymore. Why? Because we are trying to stack memory on top of compute. That is super temperature sensitive. So when you have such issues, and then we are, of course, in the future looking for three-dimensional chips, there is a problem, and that is the trapped heat. Now, clearly, heat sink has done a wonderful job and will continue, but those trapped heat are not accessible to the heat sink, and there is where you need a new solution. Let's call it X. What X should look like starts by asking a simple question, which we asked ourselves, that what if we could spread the heat before it builds up? So in that case, this X has to be a spreader, a heat spreader, that can be placed within nanometers of the hotspot, spread heat laterally and vertically as necessary, and most important of all, seamlessly integrable with silicon, metal, dielectric, insulators, anything that goes into a chip. Yes, I was talking about diamond, a material that you know very well, but used in a very different way. We were trying to solve this problem with diamond, but done differently. The way we thought about it, that can we make diamond ultra thin and reach to those stubborn hotspots where heat sink cannot touch, into the devices and chips, into boards, and all the way into futuristic 3D stacks. Now, diamond has been a material known to the humankind for long and very well known to scientists for its highest thermal conductivity. It's phenomenal when it comes to its hardness. Sometimes that doesn't work favorably, but nonetheless, it's one of the finest material that conducts heat much more than even metals can. Something that people sometimes don't realize is this is also electrically insulating, unlike metals. As you know, on a chip, you want to have this material go into places without paying a penalty like an electrical short. So these two are deadly combination, provided you can make use of them by proper tactics of integration. And the question to ask, can it beat the current state of the art, which is typically copper, which removes the heat in today's situation? Some of the breakthroughs came from our own lab, and we were trying to understand how to grow polycrystalline diamond over years, and a clear path to integration started with 3 steps. The first one, very similar to gallium nitride, diamond used to grow columnar, as you can see with very high power microscopic pictures here, that it was columnar, full of grain boundaries, which is to trap heat, full of defects. Now, our research unlocked a wonderful property. We could grow diamond flatter, thinner, and planar, and believe it or not, 3 times more thermally conductive than copper for the applicable thicknesses. That was a big step forward. But even though materials can do magic, unless you know how to integrate them on a chip, it really can be useless. And that's where we started to understand how do we synthesize diamond on chips, and for which we had to lower the temperature to a magic number, this 400 degrees C, at which it becomes compatible with silicon process. This was almost moving a mountain, but thanks to the researchers here and the resources, we could do this over time, 400 degrees C, that became the magic number when we can now integrate this material. The next hurdle was a big bottleneck, which is called thermal boundary resistance. Basically what it means is a barrier. Now, nature often gives us puzzles that oftentimes we think we cannot solve. For instance, the heat from silicon to diamond was challenged by a barrier, which we had to break through. And here we got real lucky. We were growing this diamond, we were measuring this barrier, and we found that, well, every time we are measuring something much lower than prior art has shown. We repeated, we thought that we stumbled on something wrong. In fact, it challenged some of the measurement techniques, and there came a breakthrough where we saw that the physics that existed had to be tweaked. This is a wonderful example where even physics gets tweaked by technology. Today, we can engineer those interlayers, as we call them, nanoscale interlayers, that passes the heat from silicon to diamond with extraordinary precision and efficiency. With this too, we started integrating on devices. We put it on transistors, and here is one example where you see that a hot junction dropped 70 degrees C just because of these two innovations alone. We earned a cool name. It's called the diamond blanket, really the coolest blanket you can ever find. Now, this was amazing, so we became ambitious. We said, can we make the heat go away from these complex chips where things will be stacked? We are already stacking, it'll be stacked even more. So we started thinking about putting diamond as interlayers very precisely, and here you see is the first picture of a two-tier diamond matrix, which would look like the one you see in the middle, and the evidence was clear. We mimicked actual workload that goes into a computer chip, and we saw that with this solution, the temperature dropped from 211 degrees C to 40 degrees C. Those drops are undeniable, suggesting the efficiency and the efficacy of this innovation. Now, we have sparked a lot of interest. We are fortunate that DARPA THREADS is a program that was seeded in our lab, thanks to them, that they could see the future with this research, and we are on all 6 winning teams at DARPA. We are working with the major players, you can read the names right there, to see how it can go into computation chips of future. But even more urgently, we are trying to see that where it can go else, where else can it go? So the fact that we can grow diamond on anything, and also at those temperatures where nothing gets really hurt, helps us believe that this is a widespread solution which can go to many other places in the future. Really, the possibilities are infinite. Here I end my short story of a long journey. Research is tough, but not impossible. And we find that this is the place where an unconventional idea born in a lab can redefine the future of chip cooling powered by the Stanford research. Not possible without the Stanford researchers or the Stanford resources. Thank you for listening.
Today, I'd like to tell you about some of the research that we've done over the years at my lab to break computer performance barriers. For the first innovation, you need to cast your mind back to the mid-1990s. U2 was playing on the radio, and Bill Clinton was in the White House. And if you looked at the world of microprocessor performance, what you would see is that Moore's law was in effect, transistor density was doubling every 18 months, and clock frequency was increasing at 40% per year. Performance was increasing at 50% per year, which meant that software developers had a free lunch. They could add features to their software, and they wouldn't have to worry about the performance impacts because the hardware would bail them out. All of the microprocessors had a single core, as shown by the red line. And most of architects were spending their time thinking of ways of making that single core more complex so that it could increase its performance. It was in this environment that my research lab started focusing on a project we called the Stanford Hydra chip multiprocessor. In '96, we published this paper that's become a landmark paper in which we made the argument that you should build a multiprocessor on a chip. What we showed was that if you took a microprocessor with a complex core, single core, and you compared it to an equal area multi-core processor, that the multi-core processor didn't lose too much on a single core, but was much, much better on multi-core. Now, we thought multi-core was a great idea, but the fact that you needed to write a parallel application in order to make use of multi-core made academia and industry a lot more wary and not nearly as excited as we were. Nonetheless, we were undeterred, and we decided to actually go and commercialize the idea. We started a company called Afara Web Systems in 2000 at the height of the internet boom. Data centers were running out of space and power. And we thought that multi-core could really change the situation and solve this problem. By 2002, the company had been acquired by Sun Microsystems. And at Sun, we finished the design of what became the Niagara 1 processor, shown here. It's still an impressive chip 20 years later, and it was designed for high throughput server applications, such as web servers and database servers. And everything was focused on the design on getting very high throughput and very high bandwidth. Compared to conventional processors that only had one core and one thread, this design had 32 threads and 8 cores. And it had a very high bandwidth memory interface with 4 memory interfaces compared to 1 on conventional processors. The net result was impressive performance and efficiency, performance that was 5 to 10 times better than what was available on conventional processors. So what happened between the mid-90s and today? Well, Moore's law continued, although it's now slowing down, but frequency plateaued, as shown in the green, and with it, single-thread performance. And so, and that was mainly limited by power, right? Because power constraints limited the frequency and the single-core performance. And so the only way to increase performance in an energy-efficient way was to increase the number of cores in red, so that by today, server processors have hundreds of cores, and the dominant way to design microprocessors today is using the multi-core approach. The cell phones in your pocket have multiple cores, tens of cores, and of course, all the microprocessors that run the internet are designed using the multi-core approach. So by the late 2000s, the rise of multi-core and the rise of parallel computers like GPUs and clusters made it so that the limit to performance was the lack of parallel software. And so the problem was that each of these different kind of parallel computer had a different kind of programming model. Multi-core had p-threads, GPUs had CUDA. If you wanted to program a cluster, you needed message passing. And what the problem was is that application domains that needed a lot of computation had to master all of these different programming models in order to get their work done and design high-performance software. And so this was a real barrier. And so the solution that we came up with was the idea of using domain-specific languages. So domain-specific languages have operators and data types that match a particular problem and make it much easier to write applications in that problem domain. Examples are MATLAB in linear algebra and matrices, and SQL in databases. So if you look at both of these examples, they are standalone DSLs, and they're mainly focused on productivity. And that was the idea of DSLs initially, traditionally. And our innovation was the idea of these high-performance DSLs that were focused on providing both performance and productivity, and were embedded in general-purpose languages like Scala and Python. And so the key to implementing these DSLs was to use an idea called parallel patterns. And parallel patterns allow you to understand both the parallelism and the data access patterns, and then these could be optimized, and you could generate high-performance code for a variety of different parallel computers. Examples of DSLs for AI are PyTorch and TensorFlow, and these can be used to write all kinds of ML models, models in language, in vision, in robotics. And it turns out that if you look at what you get out of these domain-specific languages, you get a data flow graph composed of operators like matrix multiply and softmax. And between these kernels are the communication is matrix or tensor data represented by the white arrows. So if you want to improve performance, the question is, how should you do it? Well, there's a famous computer architect of supercomputers who said, if you have got a vector problem, then the best way to solve that vector problem is to build a vector supercomputer. So in AI, we have a data flow problem. So if we want high performance, we need to design a data flow computer. So how should we design a data flow computer? Well, we start with these DSLs that are going to give us these data flow graphs composed of AI operators, and we're going to convert that into a data flow graph of parallel patterns that we can optimize, and then we can map that onto a data flow architecture. So the data flow architecture that we designed at Stanford was called plasticine. And plasticine is a children's modeling clay, and the architecture is reconfigurable. It's got both compute units and memory units on it, connected together in a network of switches, and you can reconfigure the architecture and mold it to the particular algorithm that you happen to be executing. And so in this example, we have the attention algorithm, which is, of course, the mainstay of all large language models. And what we see is we can map that attention algorithm in space on the chip such that data flows through the algorithm in space like cars moving down an assembly line. And what you get is very efficient communication and very efficient data access, and that is the limit to the performance of all large language models. So a commercialization of this idea is Sambonova. It's designed the reconfigurable data flow unit, and this design, the latest one is the SN40L, and it's very good at doing inference on large language models. In this example, the Llama 4 Maverick has 400 billion parameters, and the cloud service powered by RDUs is over factor of 2 faster than the service provided by other kinds of compute capability. So going forward, as Moore's law slows down, of course you want to continue to get more performance, more efficiency, and you want to have programmer productivity. And so what you see is a proliferation of both domain-specific languages and specialized hardware. And so the key challenge going forward is how do you design the right kind of intermediate abstractions and compiler technology to map these DSLs to efficient execution for AI and other computational demanding applications. So thank you.
I'm so excited to be here to celebrate 100 years of the School of Engineering. I'm Carlos Guestrin. I'm a professor of computer science and the director of Stanford's AI lab. And AI is an amazing space. And today we're going to talk about 3 interesting trends in AI today. And needless to say, AI is hot. As you can see, despite the AI winter in the late 80s, the hotness of AI has been increasing rapidly. By the way, this plot is to scale. And the value of AI in science and industry has been growing monotonically all these years. And every step of the way, around every innovation of AI, the Stanford AI Lab has been there as the key innovator in the field. Today, in the dynasty of LLM, we're seeing amazing things. Every week, some amazing new model that can do incredible new things. But it's not just about these benchmarks, it's about important applications. I asked ChatGPT to generate an image of this audience at the end of my talk, and this is what I got. Thank you very much. And beyond text and images, we're seeing incredible results in other fields. For example, this year's Nobel Prize in Chemistry is based on AI technology. But despite all this excitement, all this interest, these models can be brittle and untrustworthy. This is a query from Google Gemini where I asked, how many rocks should I eat every day? This is what I got. Raise your hand if you ate your recommended daily dosage of rocks. Jennifer, please. So the goal of my lab is to empower everyone to build accurate, trustworthy, and scalable AI applications. And we build open source software that has been used by basically every major company in the world. Today we're going to talk about these three areas and three exciting trends in each one of them. How do we make these AIs self-correcting? How do humans verify the outputs of AI? And how can we continue to learn even at inference time? Let's jump right in. The amazing success of deep learning and machine learning has been due to bringing calculus into machine learning, the idea of gradient descent. So you give me an input like, how many rocks should I eat? And a wrong output like 1 rock per day, and a correct output like 0 rocks, please. And what gradient descent says is, how can I change my parameters to go from the wrong output to the right output? The challenge today, though, is that these models and these AI applications become really complex. It's not just about a bunch of matrices. It's about a bunch of components connected together. You go to a search engine, you have agents. They all piece together in weird ways, and they're no longer differentiable. You can't apply the same math. And the question we wanted to work on is, how can we make these complex AI applications as easy as gradient descent in deep learning? And in work that we call TextGrad, which was led by my student Murthy Sekwanu, co-advised by James Zhu, which was recently published in Nature, we did just that. Our goal has been to make this easy. So here's a very simple example. Given this particular input, which lists a bunch of vegetables and asks how many vegetables do I have, the model gets the wrong output, 7, when the answer should have been 10. Now, a self-correcting AI using TextGrad can criticize its own answer, create what we call textual gradients. This is what you got wrong. This is what you can do better. And then go back and improve its input, improve the context, the prompt, in order to get the right answer back. And in the process, it discovered the magic incantation, think step by step, that gives you the right answer. But this was done automatically. This whole loop is done automatically by TextGrad. So if you consider a more complex application where we're seeing today and we want to make those easy, what TextGrad will do is something more like this. You take the output, which you want to measure in some way, and say, how can I make this output better? Well, I need better search results. So what search results do I need to make this output better? And then he goes back and says, what query should I give into Google to get the search results that will give me the output better? And this back propagation through these applications is done automatically with TextGrad. In our Nature paper, we show that this idea of self-correcting AIs using TextGrad can be applied to drug discovery, to code generation, and even to the treatment of cervical cancer. So I believe that self-correcting AIs, based on open source software like TextGrad, are going to be key to the new generation of AI applications. So our next trend is about how can we humans verify the answers of AI. Now, when I see a hallucination like this one, after I laugh for a while, I want to know why it happened. And if you dig in, you realize there was an article in The Onion, a satirical newspaper, where a UC Berkeley professor says you should eat rocks. Had I known that this answer came from The Onion, I wouldn't have trusted it. Verifying is about humans establishing trust in AIs, but this is getting harder because AIs are talking and learning and responding about a broad range of topics, which is increasing rapidly, while the capacity of individual human, me, is staying stable. Actually, I was talking about this in my class this week, and a student raised her hand and said, actually, it's going down. So if it's a question about AI, I'm pretty good at understanding its veracity. But my 11-year-old son is interested in astrophysics, and I really cannot check. So what should we do? How can we check AIs as they become more and more knowledgeable and part of everything we do? I think this is one of the big challenges of the coming decade, unless we want to defer all our knowledge to AI. And our first step in this direction has been to do what we do in academia, we're trained to do in academia, which is ground our answers on sources. But LLMs don't do a good job of this. I have young kids. I can ask a medical question. It gives me an easy-to-read, bulleted answer. But I can't verify it very well. On the other hand, I could go to Google, and I get an article from WebMD, which I know exactly what the source is. I trust it. But I have to go read the entire article and extract the knowledge out of it. What my student Teddy Worledge, along with a collaboration with Tatsuo Hashimoto, has been studying is whether there are other possibilities along the way, from extractive answers from search engines to generative answers from ChatGPT. And she studied different ways you could ground the outputs on sources. And in the process, studying humans' understanding, they see that humans prefer answers that are more generative, but they tend to have lower citation coverage, and it takes humans 185% more time to verify the answer of a generative model than it does one that's grounded on actual sources. And so what this suggests is that there's a middle ground. There's space to design new AI technologies that think about the human experience of verifying it. And grounding answers on such sources, I believe, is the first step along the way of an important journey for the decade. Now let's talk about our third trend, which is to continue to learn even at inference time. So transformers have been the key technology for the advancement of AI. And the way that transformers work is they're trained to take a sentence and predict the next word, like this one. The answer is obvious. And when they do that, they have to go back and look at every possible previous word that was ever read or said. And because they have to look back at every possible previous word, they tend to be slow. They don't scale to very long contexts. So the scientific question we want to answer is there a small, highly compact, efficient memory that can deal with very long context? So for example, if I want to ask questions about my favorite book, 100 Years of Solitude by Gabriel Garcia Marquez, I need to think about how those questions get answered. Do I have to go back and look at every single word in the book, or is there a more compact way to do it? To answer this question, we revisit the great success of deep learning. Turns out that deep learning models can remember massive, huge data sets inside the parameters of the model, parameters of the neural network. And so the question we jumped in is, can the parameters of these neural networks be not just the memory for data, but be the memory for the context, for all that great input to a transformer, to ChatGPT? Can we use parameters as a memory? And so what we're doing here is at inference time, as I read the book, I'm memorizing that input inside the parameters of a deep learning model, and that becomes the state of a transformer. We've explored this in a number of different ways, and we call it learning at inference time, which is work led by postdoc Yu Sun, who is co-advised by Sami Koyejo and Tatsuo Hashimoto. And in a recent collaboration with Ye-Jin Choi and folks at NVIDIA, we've applied this to video. So the best open source models for video can only generate short 3-second clips like this one. They're impressive. But I want to generate long, complex videos with multiple scenes. To do that, to do even a 1-minute video, I need 300,000 tokens, very long context. By using learning at inference time, we've developed the first open source model that can generate complex 1-minute videos. Let me show you an example. Curtains, please. This is a never seen before, automatically generated 1-minute video with Tom and Jerry. Here is Jerry eating some cheese, and Tom comes in and takes the cheese. Jerry is sad. He's fed up with Tom. goes back to his home, packs his bag. He's done. He leaves. Realizing what happens, Tom is missing his friend. He decides to go look for him, grabs the cheese, and goes outside. Looks for Jerry all over San Francisco. And finds Jerry, finally, sitting on his suitcase, also sad, missing his friend Tom. They come together and make up. Tom offers the cheese as a peace offering. They go back home together as friends again. Jerry comes back, unpacks his bag, and together they share the cheese and play games. This never-seen-before video was generated by the only open source model that can do it out of here at Stanford using learning at inference time. And it's not just about generating these example videos. In a detailed user study, we found that the videos we generate have better motion naturalness, better aesthetics, and better temporal consistency than alternatives that we could come up with. I believe that this idea of learning at inference time will be indispensable to scale up models to really large contexts and be able to answer the next generation of questions that we want to solve. These are some big trends that we're seeing in the areas that my lab focuses on, which is to empower everyone to build accurate, trustworthy, and scalable applications of AI. Thank you very much.
Thank you very much to Srabanti, Kunle, and Carlos. Those were some great talks and, of course, representing some really exciting work going on here at Stanford Engineering. And those were the appetizers. Now it's time for the main course. So the main course is a fireside chat between two deeply Stanford individuals whose careers have truly shaped the foundations of computing as we know today. John Hennessy doesn't need much of an introduction. He is a professor of electrical engineering and computer science here, currently director of the Knight Hennessy Scholars Program. He served as Stanford's president for 16 years, and that was a period that saw Stanford grow to become a leading university in the nation and the world. And although it was a relatively brief stop during his rise to the presidency, I have a favorite role of John's as well. That's former dean of the School of Engineering. John is also a Turing Award winner for his work on reduced instruction set computing, which transformed the way modern processors are designed, and he, based on that technology, founded MIPS Computer Systems. Jensen Huang also needs very little introduction. He's co-founder, president, and CEO of NVIDIA. And my favorite role for him, he's a proud Stanford Engineering alum. Jensen earned his master's degree in electrical engineering here in 1992, and as we all know, has gone on to lead one of the most influential companies in the world. NVIDIA has become synonymous with accelerated computing, revolutionizing graphics, powering breakthroughs in AI, obviously, as well as robotics and even scientific discovery. And John and Jensen share that they are both really nuts and bolts technical guys, you'll see, but they're also visionaries. They're deeply thoughtful about where the technology is going and how we can ensure that it continues to benefit humanity. So please join me in welcoming John Hennessy and Jensen Huang.
So thanks for being here, Jensen. Jensen just came down from another great university in the Bay Area that we're rivals in football, but we're collaborators in everything else to really lead the tech industry. So
yeah, we announced a supercomputer today.
Yeah, named for Jennifer Dowda, I think, right?
That's right.
That's great.
Yep.
That's great. That's great. So Jensen, take us back to when you were a graduate student here in the Honors Co-op program. I've heard some interesting stories, but I'd like to hear directly from you. What was it like?
Well, let's see. I was married, 2 kids, and taking Hennessy's course. That was as far as I remembered. And the thing that was really, really cool was any students of John's in the audience? Okay. The thing that's really amazing was you taught very important concepts, but you did it in a way that was very approachable and very practical. And so you spanned theory to practical engineering very comfortably in the same class, in the same courses. And a lot of people say that I explain complicated things, for people easy to understand. I just realized I learned it from you.
Oh, but that's one of the secrets of NVIDIA's success. Is they build very complicated chips, but they figure out how to make them easy for people to use.
Yeah, and also it's true for leaders. We want to do amazing things, but unless a few thousand people can mobilize and activate, they can't do it for you. And so, in a lot of ways, you have to describe complicated concepts or quite impossible visions, and somehow get people to go do something they've never done before. Mm-hmm. So if you look at the last 30 years, we started out as a graphics chip company, and that was the first accelerated computing application. And then we evolved into a computing platform as a chip company, and then we became a systems company, and then we started building data centers, and now we're building multi-gigawatt infrastructures. And along the way, we had to learn new things.
Yeah. And you really did start with that graphics idea. How did you decide that you could really make a breakthrough in the graphics arena at that time?
Well, the thing that my first board member is here, Jim Gaither, and I don't think I've ever told you this, Jim, so don't hold it against me. So we started the company with this idea. At the time, 3D graphics was hard to do, silicon graphics.
Well, silicon graphics, very high end, though.
That's right.
Very high end.
And 3D graphics was about $1 million a system. And we had this idea that maybe what we could do is reformulate the algorithms in such a way that we could put it into a PC and bring 3D graphics to at the time, PCs was barely taken off. And it was just at the beginning, Windows 3.1, it wasn't even Windows 95 yet. And so we came up with an architecture, and after working on it for a couple, 2-3 years, we realized the architecture didn't work. And so instead of the right way to do it is inverse texture mapping with triangles and Z buffers, and we did it with forward texture mappings without triangles and no Z buffers. Okay, so there's the right way to do it, and we did it exactly the wrong way, and that's the reason why it didn't work. And so we came to after all of that, we realized it turns out Silicon Graphics knew what they were doing. And hi, Reed. That's also a great story. I'm going to tell it. And so it was 2 years into it, and Jim, you remember we had a contract with Sega to build their game console, and we were on contract, and we had spent about halfway through it when we decided that the technology doesn't work, and so I didn't know what to do. But the first thing I knew we had to do was to go and tell Sega that the contract that we entered into we can't fulfill, because if we did, we would have built something for them that wasn't effective. And so I went to see Irimajiri, the CEO, and I told him this. I said, look, we started with these assumptions, and we thought this was going to be the right approach, and it turns out not to be the right approach for these reasons. And I would urge you to cancel the project with us. And there were some competitors of ours that I think had better approach, and that I recommend you working with them. And he appreciated my recommendation. And then but I said I would appreciate it if you pay me the whole contract anyways. And I explained to him that if they didn't, we'd be out of business. We had no money. We
no revenue.
That's right. And so I made him a great offer to invest in a company that had no idea how to do it right. and he was so struck by how honest that was and how straightforward that was. And he tells the story to this day. He just told the story recently in Japan, and he said he just really liked me a lot and decided to convince the Sega to give us the $5 million to invest in our company. They assumed that we were going to go out of business. They were going to write it off. It turned out we didn't go out of business.
And they did okay on their investment.
Well, they sold everything at the IPO.
They did?
Oh, yeah. Because when we went public, they went,
okay, they were smart, but not too smart.
That's not smart. That was relieved.
Yeah.
Yeah, they were just relieved we made it.
Relieved to get
And the moment we went public, they sold everything. And they left. Well, when we went public, our valuation was $300 million. Wow. It's a little bit more now, but it would be worth more than Sega.
Yeah.
The whole company.
Yeah.
Today, yeah. Even back then. And so anyhow, I then took the money. We came back and we asked ourselves, so what are you going to do? And I said, well, we got to go learn how to do 3D graphics the right way. And thankfully, some of our employees today, while they were at Silicon Graphics, wrote some really nice textbooks. And so I took a few $100s and ran down to Fry's Electronics, and I bought 3 textbooks. And I brought it back, and I said, you get one, you get one, you get one. And let's get to it, shall we? And now I know it sounds completely ridiculous, and now NVIDIA is the most impactful, we're the largest 3D graphics company in history.
Yeah.
And we've made more contributions to 3D graphics than any company in history. Yeah. And that tells you something. And in fact, it's one of my favorite moments because it says that even if you don't know how to do something, with the right people, right motivations, and not going out of business was a good motivation, but in our case, the right motivations, we could reinvent it. And so we just read through the textbook, and we said, from first principles, how would we do it today? And we completely reinvented the way graphics is done.
Yeah.
Just by studying the same ideas, but applying first principles, how the world would, how would we implement those ideas? Well, that skill set, that belief in yourself allowed us to build self-driving cars. We just went into production with Mercedes, do robotics, do artificial intelligence, go into scientific computing. Now we're doing, we're probably doing more in quantum computing than just about anybody. And all of these, no idea how any of this stuff worked. And so these days I don't even have to go buy textbooks. I just ask.
Just ask your team because you've hired such great people.
Well, first I asked ChatGPT.
Don't always trust it. It may tell you to eat rocks.
No, you always do deep research. Don't ever get the single response. But
what I love about this story, though, lots of young people think the road to success for startups is smooth and straight, and it rarely is. And I think it's a great indication of that.
Yeah, willpower matters a lot.
Yeah.
And belief in yourself, and go back to first principles always. And when you do that, when you learn, when you read somebody else's textbook, but you go back to first principles and you take the context and how things are different today and the enabling technologies are different and the tools are different, everything's different. How would you reapply, how would you resolve those same problems with different tools?
Yeah.
And it turns out there are a lot of different ways to solve the same problem.
Same problem.
Yeah.
Yeah, absolutely.
Yeah.
So talk about, I mean, clearly one of the most brilliant things NVIDIA did was creation of CUDA and really its establishment. Tell us about the origins of why did you make that decision? Why was it so crucial?
Well, we came to the conclusion that computer graphics was rendering the images, but statically is not a good idea. You want to bring the world to life, and so you're trying to create a virtual world. And inside the virtual world, you want to do physics. And so solving physics was actually the first problem we wanted to solve for video games.
Yeah.
And well, how do you solve physics? Well, solve physics, you know. And so how do you do, you know, computational fluid dynamics and particle systems, and that was the inspiration of the first. And now the question is, how do we refactor that GPU? And we knew we could do parallel computing, and how could we refactor the computation in such a way that we can express these algorithms, but more naturally instead of using OpenGL or Direct3D. And so we came up with the idea that maybe we'll do C for graphics. And so we re-expressed the programming API in a higher level of abstraction. But we came to the conclusion that these parallel algorithms really want to have shared memory, and maybe the way we want to express it is a little differently. And that led us to work on OpenCL. And then OpenCL, while we're working on OpenCL, meanwhile, Stanford saw the work that we did with CG, and some of the students started playing with CG, and they were working, and then they extended it to Brooks, and then Brooks, the students here were interns at NVIDIA. Meanwhile, you know, minds meet, and before you know it, this CUDA came along, and so. But that's kind of like mixing and matching and playing in that area. But the problem we were trying to solve was a good problem: computational fluid dynamics, particle physics, and the fundamental parallel computing problems kind of emerged from there. Well, after we did that, we came up with some good ideas. Then the question is, what big problems can we go solve with this? And that led us to supercomputing, led us to, you know, CT and image processing and those kind of things.
But it's a big leap going from being a graphics company to being a supercomputer company. I mean, that's a big leap. It's a different business. It requires a lot more system expertise, more software expertise. So how did you think about assembling a team? Because that really had to change the talent.
John, is all the same way. You know, so first hey, we could do this, you know, and so it's like, it always starts kind of like this. Hey guys, we could do this, and we could do, and so you start by dreaming, and then the next logical leap is, well, how hard can it be? I always start every meeting with, you know, hey guys, we can go build self-driving cars. It's sensible. We have computer vision now. You know, planning algorithms are fairly well known. And let's go. And then somebody goes, we don't know anything about cars. And I said, well, how hard can it be? And so I think the clincher on that one is, my mom can drive.
Yeah. Actually, humans are pretty good drivers when you look at it.
I know. My mom shouldn't, but she can. and so how hard could it be? And so the supercomputers were all the same thing. You know, AI, how hard can it be? You know? And so you just go into it.
Yeah.
The question isn't so much, can we do it? I assume we can do it. Almost everything. You know, quantum computing, how hard can it be?
Quantum computing?
It's quite hard. But, you know, but how hard can it be? You know? And so we got plenty of time. And so the real test is, one, is it incredibly hard to do? Because if it's incredibly hard to do, and it's going to take, say, 20 years, then we're not that far behind.
Right.
You know, the fact that we only started today.
Yeah.
Nobody's that far along.
Yeah, nobody's that far along.
And so how far, you know, and so one, I like to choose problems that are really, really hard to do. And the problems that are really hard favor not the most intelligent, favors the most persistent.
It helps to have smart people be persistent. But you're right, persistence, especially on really hard problems.
That's right. Yeah.
It's really key.
Yeah.
It's really key.
And so it becomes a self-selecting thing, and amazing people want to do it. And so anyways, one, how hard is it? And then the second is how consistent is it with what we're good at? And the way I test it is, if we didn't do it, is it going to naturally get done anyways? Mm-hmm. And if it's going to naturally get done anyways, let's let somebody else do it.
Huh. Interesting.
Yeah. And so I like to do the leftover work, the work that nobody else wants to do.
And when you pick a really hard problem like that, do you ever decide we're not making enough traction, we're not making enough progress, it's time to cut my losses?
Usually it's the other way. And this afternoon, right before I came, at a meeting, and we've been working on this in this area called digital humans. Mm-hmm. And I started the project. The team. I named the project. I started the project. Assembled the team inside, and we've been working on it for 5 years. And then today, I told the team that I don't think we need to do this anymore. Hmm. And the reason for that is because the assumptions that we used in starting the project and the technology that we thought would be enabling for it turns out not to be. And generative AI is doing it so well now that, quite frankly, it's a bit of a commodity. Yeah. And if we don't do it, it's going to get done anyways. Yeah. So why don't we take this amazing team and go do something else? And I've got a list of 3 other things we could go do. And so that's usually, we usually leave a project because it looked too easy. Yeah. Not because
or too commoditized. Right?
That's right.
Too many other people will do it. So you won't have a real advantage the way you've had in the core.
Well, if it's a big market, why don't we go capture our share?
Yeah.
And that's always the wrong thinking. And the reason for that is because if you want to assemble and attract the world's best people to go do their life's work, who wants to wake up in the morning to go take share? It's a weird idea. I've never really understood. How do I get myself up in the morning and go, you know what? They have 17% share and I just want to take 3 of it. Yeah. It's really super angry to me.
As opposed to, I want to be the leading company in the space.
This has never been done before. Let's go do it. Yeah. And so we kind of, not everything that we do turn out that way, but we leave it. If it gets to a point in the beginning, almost everything that we do in the beginning is a $0 billion market, so nobody's there. But at some point, 4 or 5 of the things that we've done in the past, by the time that we ramp up to $1 billion or so, there are 4 or 5 players. And I'll tell the team, tell the company, guys, I know it's $1 billion business, but there are other $1 billion businesses. Mm-hmm. And let's go do something the world's never done before. Yeah. That's how you attract and that's how you retain amazing people like Bill Dowdy. Because they don't want to go work for share.
They want to do
do original work. Yeah. And it turns out it's possible to do both. To do great business that nobody else does.
Yeah. One of the things I found really interesting is NVIDIA is really at a turning point in the industry. I mean, the industry became horizontally cut up, right? You had Intel down here, you had Microsoft down here, and then you had the PC designers and the server providers. Your vertical stack, you go right all the way up to the hardware, from the chips to the hardware. Do you think this is been key to your success and key to the innovations you've really
done? Completely. In fact, I was taking your course at the time of the beginning of the PC revolution, and in fact, the PC revolution, which is horizontal, is unique. It's not
what traditionally existed before that, right? IBM was a vertically integrated company.
It's not the way it is. Yeah. Look at the clouds; it's all vertically integrated stacks. Right. And we made the right observation that the world is not going to remain like PCs. The PC is unique for a lot of good reasons, and so the thesis is that there won't be a Microsoft for AI. Mm-hmm. There won't be a Microsoft for accelerated computing. Mm. And the reason for that is because it's going to take so long for accelerated computing to take off. Yep. Because the alternative is so good. The alternative was Moore's Law. Yeah. The alternative was multi-core, many-core. The alternative was do nothing. And nothing was pretty good.
Right.
You know, when doing nothing doubles your performance every year,
Right.
that's pretty good.
It made it easy. It made it easy.
Yeah. And I used to explain to the company that the best way to screw up when you're sitting on top of Moore's law is to change.
Right.
To do nothing is the best way. Just stay on the rocket ship and let it take you. But eventually, laws of physics is going to get in front of you, and you're not going to get those factors, and that would be our time.
Yeah.
And we better be ready for that to happen. And you know, I thought it was going to take 5 years. It took 20, but it's close. And so anyways.
But it did happen. It did happen.
That's right.
Mostly because building the whole vertical stack takes time.
That's right. And for industries that took that long, for what reason would somebody build a software layer on top of you?
Right.
What's the economics on that?
Right.
There's no way that you could build a business where the volume is so tiny.
Yeah.
And build a horizontal stack.
Yeah.
And so we assess the strategic dynamics properly, and as a result, we built a whole stack, one industry after another industry after another industry, and by the time that it took off, you know, we've been working on these stacks for 20 years.
But perhaps where you're really unique, most of these people that have gone back to vertical integration have gone from the top, from the software stack down. You started with the chip side and worked your way up.
We started from the chip side and work our way up. We're super good at algorithms.
Right.
Super good across the stack.
Right.
And accelerated computing is unlike general purpose computing.
Right.
You can't write an algorithm, C, compile it down to the instruction set. You've got to go domain specifically, one at a time. And the number of domains of computing in the world, surprisingly large.
Yeah.
And if you want ultimately to seem like you run everything, it's because you did it one at a time for everything. And today we seem like we run everything, not because we run everything, it's because we spent so much time, did it one layer, one stack at a time.
It's a good point.
Yeah.
So share some of I've heard you talk about your vision for what's going to go forward in the future of computing and scientific computing, AI, this whole thing. Share some of that with the audience.
Well, the thing that's really, obviously AI is important, but there's a couple of different ways to look at AI. You know, perspective matters a lot in strategy. And insight matters a lot in strategy. When AlexNet came, obviously computer vision was incredibly effective. But we were good about reasoning back to first principles. What are we seeing here?
Right.
How scalable is this? What other problems can it solve? Mm-hmm. How does this impact the computer architecture? What kind of systems would we build if AI were machine learning or deep learning at the time were to scale much greater? How does it change the way software programming works? Machine learning is obviously different than hand coding. What is the difference? What is the change to your enterprise, your corporate R&D culture, tools, infrastructure? What are the problems we can solve with this that we couldn't solve before? What are hard problems that we can now solve? What are problems we solved that's unnecessary to go resolve? What are the problems that we have solved that we can augment now with the... And so we just reason through everything. Over the course of time, we always break things back down to first principles, and we came to the conclusion, everything's going to change. Mm-hmm. And so we went back to the beginning again and said, what is the implication to our GPU? Our GPU for AI and our GPU for computer graphics is related, completely different. Where, in what way, what kind of, the system architecture, how would it change? NVLink came out of that. Recognition that we have to be a networking company came out of that.
Right.
All of the different, we invented this thing called Megatron Core, which really revolutionized the way people did large-scale training. Recently, we announced an operating system for AI inference called Dynamo. And so anyways, you break everything back down to first principles. And then the next thing that we did was really good. If we're going to be a machine learning company, we're going to be an AI company, at the time, deep learning systems company, well, we have to learn how to use it ourselves. We can't wait around for somebody else to be a customer of this system. We have to be our own customer. And so I made at the time, we could barely afford it, built our first supercomputer. And it cost our company several $100 million. And that was the largest single investment we ever made. And that was, you know, and we reasoned through it and said, this is ultimately an investment we have to make. If we don't make this investment, how can you be a software company? How can you architect a system you've never built?
If you've never built it, yeah.
How can you offer to build this thing for other people if all you've done is made PowerPoint slides? You know, and so we went and built it, developed the software for it, and then the next thing was well, how do we know that we're any good at this? And so we started our own AI, you know, R&D team, and the application I put to work was languages and self-driving cars. And we dedicated ourselves to be world-class at doing those things, and today we're very, very good at it. And so that entire layer from building the AI infrastructure, and building all the necessary technology underneath forced NVIDIA to be good at it. And then the next thing, we had no AI researchers, and Bill's background is not AI.
Right.
And so the answer is very simple. We just got to go get some books.
Maybe hire a few people, or
well, who would come work? What AI?
Who would come work
exactly
at that point?
What at that time? What AI researcher would go work for a computer graphics chip company?
You're right. Well, it was a little more than that, but anyway.
But in a lot of ways, it was
it's a good point.
Because at the time they were all going to Google, they were all going to
DeepMind, right?
Exactly. Who would come to NVIDIA?
Yeah.
And so I said, how hard could this be?
Yeah.
Let's just get, how hard could...
I have the hardware, guys.
I said, how hard can this be? Let's just get to it. And then, you know, all over the company, we had researchers who didn't know anything about AI. I said, how hard could it be? And so we just had everybody start working on it. And the area that we dedicated enormous resources was computer graphics.
Yeah.
We said, if there's one company in the world that's going to bring AI to computer graphics, it would be us.
Of course.
And therefore, we had to start with us, reinvent our company. And so we just started going at it. And then I discovered something that was very obvious. If you want to attract great researchers in machine learning, you need to have a machine. And it turns out I had a machine. And no users, but I have this massive machine. And went out and, you know, attracted one researcher after another. And today we have a world-class team, unbelievable team.
Yeah, unbelievable. Unbelievable.
How hard could it be?
All the way, how hard could it be?
As it turns out, it's extremely hard.
Yeah. Yeah.
That's why it took so long. That's why it took so long to do.
You know, I think one of the things that really shines in your answers, and certainly in the history of NVIDIA, is this is a company that is deeply committed to technical leadership. It's kind of foundational for the company and always has been. And you see companies often lose that as they grow, right?
Yeah.
But
we really seek out the really, really hard problems.
Yeah. Yeah.
Oh, look at quantum computing, and so there are, you know, 4 or 5 different ways of doing it. Superconducting, photonics, right? Neutral atoms. I mean, there's lots of different ways of doing it. And so the question is, you know, we're a computing company, and arguably one of the most consequential computing companies of all time. Is quantum computing in our future? And the answer, of course. But do we have to build a quantum computer? Absolutely not. And so we decided that we would be the company to work with every quantum computer company in the world, because obviously it won't just be quantum standalone, it'll be quantum classical. And we could be, and if you're going to have a supercomputer, a quantum computer there, let's just face it, you're not going to feed it with a phone. And so it's likely that it's a supercomputer that does the pre-processing and the control and the error correction and post-processing. And so it's sensible that it's us. And so we decided to go build a whole stack for quantum computing and figure out what algorithms we can go contribute to. And we created an architecture for quantum classical. Today we're working with every company in the world in quantum computing. And so as a company that does absolutely no quantum computing at all, it is very likely we're, you know, one of the most important quantum computing companies in the world.
Well, now you see why NVIDIA is such a great company and why Jensen is considered the star CEO of Silicon Valley.
How hard could it be?
Let's thank him.
Thank you. Well, it turns out It's extremely hard, and it helps if you went to Stanford.
And we're gonna have a short video message from a friend of Jensen and mine and one of our other distinguished alumni.
Thank you.
Hello, I'm Morris Chan. I'm the guy that made a lot of semiconductor chips for everybody to use. First in the United States, then in Taiwan. Now we'll make lots and lots of chips again in the United States. Today we celebrate the 100th anniversary of Stanford Engineering School. I was a PhD student in the school in 1961 to 64. I had started to make chips in 1955. So by 1961, I was already an experienced chip maker, but didn't have a PhD degree. The company I worked for at that time decided that I should get a PhD. They offered to pay all the tuition and expenses and still pay me full salary while I was getting my PhD. They asked me what school I wanted to go to. In the early 60s, Stanford already had several well-known scholars such as Gerald Pearson, John Linville, and John Moore, not to mention Shockley, who was a guest lecturer here. So I said, without hesitation, Stanford. I spent 2.5 hard-working and happy years here. I was a first-generation chips guy. We worried about how to make chips, how to make each chip contain more transistors. The generation after us, of which Jensen Huang was an outstanding example, worried about how to make chips more useful. The last 100 years were an exciting time period for electronics. Successively, mainframe computers, PCs, laptops, notebooks, and handsets changed our lives. And now AI, artificial intelligence, will change our lives even more. Semiconductor chips were the backbone of every one of those technologies. I congratulate Stanford Engineering School for having played a pivotal role in this exciting age. I also salute John Hennessy and Jensen Huang, who introduced me to this happy occasion. Thank you.
I'm John Levin. I'm the president of Stanford, and I get the honor of closing out this event. And I just want to, first of all, thank all of you for coming. Thank the faculty whose talks you saw, who were incredible. By the way, the Stanford School of Engineering, that was 3 of the faculty whose work you got to hear about. There are 280 faculty in the Stanford School of Engineering. So just think about the work that's going on every day there. It's extraordinary. And I want to particularly thank John and Morris and Jensen for coming and talking. I think the 3 of them, as much as any people who've been at this school, exemplify all of the characteristics that have made the Stanford School of Engineering the greatest engineering school and greatest center of innovation on the planet. The incredible depth of technical expertise, the entrepreneurial mindset, the persistence, and the scale of ambition. And, Morris was at the Stanford School of Engineering in the 1960s. Jensen was in the 1990s. So that says probably somewhere out here in the audience or at the school right now is the next Morris Chang or Jensen Huang, one of our students. So I hope one of you will become that person. Thank you all for being here. It was a terrific event. Thank
you, President Levin, for your closing remarks. it's my honor to really say the last closing words. So thank you to everyone who contributed to today's program. I think we have our faculty speakers over there. We've got John and Jensen, Director Rice, President Levin, and all of you for coming to join us during this very special centennial year. This has really been a celebration of Stanford's legacy in computing, a fascinating look at the road ahead. So enjoy the rest of your evening. Thank you again for coming and for being part of our centennial. And here's to the next 100 years.
That AI will do enormous